I really feel like
Right?
it was
It's
out
like
there.
these
Yeah.
things that once seemed crazy become like real life thanks to people being willing to take a gamble on it, support it.
Welcome to Holy Shift, Biomedical Breakthrough Shaping Tomorrow. What is biomedical engineering exactly? It's about engineering solutions that improve human health, from new medical imaging tools to personalized cancer treatments. Holy Shift reveals the people, passion, and purpose powering the future of biomedical research. How can biomedical engineers help people that live with severe paralysis get some of their independence back? Enter the brain-computer interface, a system that reads out signals from the brain and translates them into movements of a helper robot or synthetic speech. Our guest today is Dr. Chethan Pandarinath, an associate professor in biomedical engineering and neurosurgery at Emory University and Georgia Tech. He works on this sci-fi technology to help revolutionize the way people live with paralysis. So welcome to Holy Shift, Biomedical Breakthrough Shaping Tomorrow. And we're very excited. We have offices down the hallway from each other.
Yeah, thank you so much. I was hoping you wouldn't say that because then people will think you're going to go easy on me.
Totally not. It means I go harder
Oh,
on
no.
right? That's what it is. That's the deal. So
All right.
why don't you tell us about yourself and why you're here today?
Sure. So, as you know, I'm Chethan Pandarinath. I'm an associate professor of biomedical engineering at Emory and Georgia Tech. And I work on neuroengineering, which is a type of engineering that works on kind of understanding and repairing the brain.
The brain. Okay. So we're going to peel this back a little bit. Tell us, okay, my favorite question is this. I just have to dig in directly to it. Is this what you wanted to do when you were 5 years old?
Ooh, good question. Thinking back, I don't know that I wanted to do anything like specific, but I knew I wanted to do stuff that was like kind of sci-fi and like high-tech and interesting.
Okay.
Right? Yeah. Originally, in undergrad, I was doing all sorts of different things, computer engineering and physics. Then I went to grad school thinking I would work in quantum computing.
Ooh, what was the tie to quantum computing at the time?
It just sounded really cool.
It does sound cool. Yeah.
It was somewhere
totally
in
does.
between like computing and physics.
I also just wanted to say that quantum
quantum computing.
Exactly,
Yeah.
exactly.
I mean, it's probably the future. Probably. When I was in grad school, so my dad has Parkinson's disease, and he'd been diagnosed for a while, but when I was in grad school was around the time we started really noticing, his symptoms.
Yeah.
Like, I remember my mom called me one day and said, "Hey, your dad's like stuck at the gas station." And I was like, "Oh, is like the car not working?" And it was just, no, he couldn't drive anymore. His Parkinson's was getting to the point where, he just didn't have like good control of his body at times. And that really, started like affecting him and of course affecting me when like one of the most influential people in your lives starts to have problems with their body. So you might be familiar with Parkinson's, but one of the treatments for Parkinson's is something called deep brain stimulation.
Yes.
And that's where they take an electrode, which is, a device that can emit current, and put it like deep into the brain, into a place that's known to be like really important for movement. And what we saw was, you could literally now, when you turn this device on and start stimulating with like a tiny bit of electrical current, you can just see like my dad's ability to move completely change, right? Like he has very little control of his movements, and all of a sudden, like that, he's able to move again. He's able to eat well and things like that. And so I had always thought like, biology, this like wet stuff, I don't understand it. Computers, I can do that. Physics, I can do that. But then I realized like there are things we can do with like the things that I know, like physics and electrical engineering, that can actually like really dramatically change people's lives. And so that, was a pretty big sign that like, oh, I can still kind of do interesting sci-fi stuff and maybe also help people at the same time. So
Okay. Cool. Yeah. Now this is cool. So where were you at in grad school?
I was at Cornell.
Okay.
Yeah.
Okay. And so you had this little shift. Did it change your PhD thesis and what your focus was on that? So what did you focus on?
Completely. So yeah, I was working. Cornell has a great program in like manufacturing computer chips, like nanofabrication.
Okay.
And so that's where I was. And then all of a sudden I'm like, I want to study this brain thing, and
Right.
nobody there knew what I was talking about. And so you know, in grad school, you know, you've got to find a lab where you can do your work. And I just kind of like left all of that stuff. So Cornell is in upstate New York, in Ithaca, New York, and they didn't really have a lot of research in what I wanted to do. So I went to Cornell's medical school, which is in New York City, you know, quite a ways away, and just completely changed what I was doing. Started working in a neuroscience
Which is a
lab.
huge decision and pivot at a period of your life where you have spent a lot of time and resources. And I think most people don't understand how difficult it is to get into a lab to begin with. And then to start work and then shift to somewhere else. That was a huge commitment.
Yeah.
How many times did you sit back and say, am I making the right decision?
Well, yeah, I think thankfully I don't think things through well enough. So I was like, oh yeah, this will work. I'll try it.
Why not? Right.
But yeah, I mean, if any one of my students right now was saying, hey, I'm just gonna go to this other campus, join a lab I've never been a part of, and completely change my career, I'd be like, whoa, let's stop. Let's think about this. But you know, it worked out.
Okay, so you shifted over and you went then to Cornell Medical School and joined a lab there. What was your initial, did your major shift there focus on Parkinson's specifically to drive what you were doing next, or what did that look like?
Yeah, actually, yeah, not at all. So I was, I knew I was interested, like I needed to learn about the brain, and I didn't know anything about the brain, so that seemed important. So I went to a lab that was studying the eye, which sounds a little different. It's obviously different, but you know, if you think about it, the eye is like the first place that we get information about the world that's sent to our brain. So in the back of your eye, there's a little piece of tissue called the retina, and the retina sends that information to the brain about like the visual world. And so it's one of the few places in our bodies and our nervous systems where you kind of have this like bottleneck. You have like signals coming in and they need to be translated and sent to the brain. So it's a great place to learn like kind of the language of the brain. How does the brain like communicate? How do pieces of the brain communicate with each other?
Right.
And so that's what I did, was kind of study how are signals, you know, you can kind of stimulate, like turn on little spots of light on and shine them on the retina and see what comes out. And like learning kind of the language.
And see how the brain reacts to
Exactly.
it, and perhaps how different brains react differently, or how different stimuli like highlight different areas.
Exactly. Yeah.
Okay.
And one of the cool applications of that work, which I started getting into in the end of my PhD, was, you know, there are a lot of people that unfortunately become blind through things like macular degeneration or retinitis pigmentosa. And it turns out, you know, the retina, this thing in the back of the eye, has a few layers.
Okay.
And often it's like the front part of that will sort of degenerate, that will go bad. So the thing that actually receives the light goes bad, but then the rest of the retina is still there. So if you can put little electrodes on the retina, you can stimulate it and then send messages to the brain. So even though the retina itself isn't kind of functioning well anymore, there's pieces of it that are intact, and you can use that to still kind of communicate with the brain. And so there are a lot of companies that are working on ways of, you know, restoring vision for people who are blind.
Wow, which is so huge. Has anyone ever asked you this question? If you had to lose what sense, what would you want to lose? Right. And when people have said that, I've always said vision.
Really?
Over, but some people are like music people, they want to hear or something like that. But there's so much beauty in the world that to lose that, and I've known people that have had conditions that have been degenerative or slowly degrading and getting worse. And I think it's really sad to know that they're going to lose something that they had and depended on.
Absolutely.
And it brings so much joy and passion in people's lives. So you got interested in doing this work, and is that what you did your PhD on?
That's right.
Yep. How did you then get from sunny New York City, cold New York City, to Atlanta, Georgia?
Yeah. So in between I went to the Bay Area. I did a postdoc. So a lot of times after your PhD, you'll do something called a postdoc, which, so I come from a family, like there weren't any scientists in my family.
Oh.
So, my mom was like, okay, you got your PhD. Like, is that enough degrees? Do you really need a postdoc degree? And I'm like, oh, sorry, Mom, I'm not even getting a degree this time.
Right,
So
exactly. I got my terminal degree. This is just
we're done
extra
with that.
credit.
So yeah, I did a postdoc at Stanford where I worked with a professor and mentor, Krishna Shenoy, who is really one of the few people with kind of an electrical engineering background that worked on kind of studying the brain and building devices to help people who are paralyzed.
Okay.
So that was like my first introduction. Now we're getting closer to something like Parkinson's.
I didn't ask. So then that was electrical engineering. What did you get your undergrad and PhD in? What engineering was that?
So computer engineering for undergrad and electrical for the PhD.
Okay. I love this because a lot of times, we're on a biomedical engineering podcast, how engineering applies to the human body. But one of the cool things about biomedical engineering is it touches all these other engineering disciplines.
Absolutely.
And by working with people who have all these different backgrounds, a lot about what makes the magic happen. So that's fascinating. So now you go to Stanford and working with someone from electrical engineering
That's
on
right.
this challenge.
Yeah, I mean, speaking of that, like somebody asked me, like, when did you know you wanted to become a biomedical engineer? Like, I've never tried to become a biomedical engineer.
Yesterday?
Right? I've tried to do a lot of other stuff, but it turns out like biomedical engineering is exactly the right place for what I want to do. So kind of discovered that along the way.
Okay, so you're in Stanford. You're doing your extra credit postdoc in electrical, starting to work on paralysis.
That's right.
Okay, and then how did that journey take you to then Atlanta and the work that you're doing now?
Yeah, so that's kind of where I started working on these devices called brain-computer interfaces. So these are devices for people who are paralyzed, like you're saying, and people can become paralyzed from things like spinal cord injury or stroke. Or amyotrophic lateral sclerosis. If you've heard of
what? No. What was that?
If you've heard of Lou Gehrig's disease,
yes.
it's maybe like one of all neurodegenerative diseases are bad, but it's a really rough one where over time people gradually kind of lose control of their bodies. And in all these cases, spinal cord injury, stroke, ALS, it's like the brain effectively becomes disconnected from the body. So people will have trouble moving their arms and hands and fingers, or some people will have trouble speaking. Mm-hmm. And, the crazy thing is, like, the brain's effectively disconnected from the body, but they can still think about moving, right? Like, I think about moving and my hands moving around.
Right.
They think about moving.
And nothing happens.
Nothing happens. So, but what we've learned is you can place electrical sensors in the brain, in parts of the brain that control movement. And even though the brain's kind of disconnected from the body, and maybe somebody had, a car accident 15 years ago, and they haven't been able to control their hands since that time, we can still pick up on electrical activity in the brain, these like neurons talking to each other as the person thinks about moving their hand or their arm. And then we can decode that, we can translate that activity and do something useful for them, like move a robotic arm or control a computer, or if they're having trouble speaking, maybe output like a digital voice, synthesize speech for them. So it's really, kind of fascinating that this thing, these are horrible conditions, right? They really, really affect quality of life, but we're starting to develop ways of helping these populations. So it's a really exciting time.
Well, that's inspiring. It's impossible to hear that and not be inspired. So then we stole you into Atlanta, and you're doing research now. So you finished, that postdoc. Tell us about your lab. Maybe tell us a little bit about the people that work with you within your lab, and what's the hot topic right now.
Absolutely. So we're a part of something called the BrainGate clinical trial. It's a collaboration between a few different institutions: Emory and Georgia Tech, Stanford, where I was before. Massachusetts General Hospital, or just a few. And the basic idea, it's a clinical trial, so we work with people who do have these conditions. So, here at Emory, we work with somebody who had a stroke, a really devastating stroke called a brainstem stroke.
Oh, wow.
And so we work on things like, so we worked with neurosurgeons here at Emory. I have a really close collaborator, Nicholas Aoyong, who's a functional neurosurgeon, and he implanted electrical sensors into the brain of this person that has had a stroke. And so we worked with her to develop new assistive technologies, things like restoring her speech, so she can, attempt to speak, and we can try to decode that and figure out what it is she's trying to say. Things like controlling computers. And if you think about these ideas, you probably get the sense that we're combining a lot of different disciplines.
Yes.
Right? The brain, obviously. So we have neuroscientists in the lab. There's a lot of electrical signals, so electrical engineers, computer scientists.
Okay.
One of the biggest challenges is that we're sensing electrical activity from the brain, and the brain doesn't speak English.
Right. Yeah, exactly. I was just thinking about that little translation piece.
Exactly.
It's so hard.
Exactly. So one of the key things we're always facing is how do we translate the brain's electrical activity into what it is the person wants to do, right? And honestly, one of the biggest changes in our lives in the last few years has been like artificial intelligence, ChatGPT, large language models, and it's super useful for us, but it's also super useful for translating, doing this kind of translation problem. It's almost like going from French to English or something, but going from electricity to what it is the person wants to do. Exactly.
Yeah. Okay. So in thinking, so then you have these team members with different backgrounds and things like that. What is right now the key project? Because I know you're also working within the lab, and then you're also working out in the world for a company on some different projects. Tell us about both of those key projects.
Okay, so within the lab, what are the key projects? So, this idea of restoring somebody's ability to speak it's something that's kind of only become possible in the last 5 or 10 years. And so it's a very rapidly growing field, and that's one of the key things that we work on. So just for example, we had a study last year with our collaborators from Stanford working with this research participant here in Georgia. And one of the things we asked was, so what does it look like in the brain when she thinks about speaking?
Yes.
Right? When she attempts to speak. I think one of the most interesting things, this has some interesting kind of privacy implications. So, we can ask her to speak the word camera, right?
Okay.
And we can see a certain pattern of electrical activity when that happens. We can also say, think about the word camera, but don't try to speak it.
Ooh.
And in these parts of the brain that are thought to control the movement of your mouth, the movement of your
vocal
tongue,
cords,
things like that, exactly, your vocal cords, even when you're not trying to speak, we see activity related to what you're thinking about.
Oh.
And that's a pretty big deal, right?
It is.
Especially if we think about how to build these devices, get them into people's homes and people's lives. I can think right now about things that I don't want to say out loud, right? Like, I would feel pretty silly if everything I was thinking about was just broadcast to the world.
Right.
So what we've learned is, these patterns of electrical activity in the brain, there's some similarities between when you try to speak and when you are just thinking. Mm-hmm. But there's also enough differences that we can tell the difference. And that's a really critical thing, because when we build a device, we can say, here's the stuff you want to say out loud, here's the stuff you want to keep internal, and we can kind of build a wall.
You know what I'm thinking of is people, I think, have heard of individuals who have something like Tourette's. And I would think of like something like Tourette's might be a breakdown in that functioning to be able to do that, or just, some issues in that. I mean, this is not a direct translation, but like an idea of that would be something similar to that.
I wouldn't be surprised if that's, it's very likely to be what's going on here. Something like that, where there is a breakdown between kind of what's meant to be internal and what just comes out.
Yeah,
Absolutely.
yeah. Okay, that is amazing. Should we do a plug right now how important bike helmets are? You and I tell people, well, also, not because of any accidents people have had, but because in my triathlon days when I would see people cycling, okay, and having spent my career in the medical health space, I've said to individuals, the brain is the one thing that makes you uniquely
Absolutely.
you. And so protecting that. And so I think this even more protecting this when you think about the power of when other things are not functioning, how you can utilize that one very important of what makes you you and me to overcome that.
Right. Yeah. Now may be a good time to turn directly to the audience and say, wear a bike helmet.
Yes.
I think you're absolutely right. I also had some experience recently, as you know. I had a crash on my electric skateboard, unfortunately, and it was pretty bad. Had a concussion and some fractures and things, and it was definitely one of those times where you realize just how, like you're saying, the brain is what makes you you. There were a couple days after the accident where, my wife was like, "You're a lot more irritable than you usually are," and she was absolutely right. I mean, the fragility of the brain is really something we should keep in mind.
Yeah. Okay, this is fascinating. So then, how does this tie to the work you're doing out in the commercial setting? So
it's interesting the stuff we're doing. So I work with people are familiar with Meta, Facebook, Instagram, that company. One of the things they're working on is augmented reality.
Okay,
so, the idea, like, we spend a lot of time on our phones, and we have a little screen, we're interfacing with it. What they'd like to do is, integrate that with your glasses. So instead of, having to carry around a phone, you're wearing glasses. When you want something, like you get a message, maybe there's a little display within the glasses. But when that happens, I mean, are you going to poke your eyes to try to type out your text message?
Right.
That's what they're trying to avoid. So they've also developed a device that can go on your wrist and sense. So when I move my hand, when I move my arm, my brain is sending signals down to my arm, and then that's activating my muscles. And when that happens, there's a lot of electrical activity at the wrist. So every time I'm moving my fingers, there's a lot of electrical activity here that we can pick up. So the same problem that we're trying to do kind of in the brain on the academic side of understanding the brain's activity, they're trying to do for kind of commercial applications, which is you want to type out a message, maybe you can just pretend you're holding a pencil and write.
I see.
Your handwriting, and if we can take this electrical activity at your wrists, we can take this complex pattern that's your handwriting and turn it into the characters you want, and you don't have to carry around a phone, you don't need to tap on anything, you can use it whenever you want. So that's the main problem that we've been kind of working on, is how do you measure electrical activity at the wrist and turn that into control of a computer, basically.
Yeah. Which I can see also the medical advantages of that as well, which I think that's the cool piece about these things can be used in a variety of ways. And we need thoughtful scientists who are working on it to help us continue to work in a for good mentality.
Oh, yeah.
So
Absolutely.
speaking of this work, the corporate work is, of course, funded by entities that have funds to be able to do that. However, the work in the research lab and the academic setting is very different. So can you talk about your work in particular? Who do you need for funding, and what are the kind of the pros and cons and challenges of that?
Yeah, that's a great point. I mean, we're talking about technology that really kind of has the potential to change people's lives, to help a lot of people.
Right.
And our ability to build that technology, to pursue it, really, most of the funding for that comes from the federal government. So we've been really fortunate to get a lot of NIH funding because, the NIH believes in biomedical research and translating that. It's becoming harder these days, unfortunately, but we have been fortunate in the past to get NIH funding. Another big agency is DARPA, the Defense Advanced Research Projects Agency, which is kind of like the out there arm of federal research funding. So they kind of see brain-computer interfaces as something that's like wild and out there. Maybe these days it's not out there enough.
Yeah, I was thinking that, but maybe 15 years ago,
Exactly.
It did really feel like it
Right?
was
It's
out
like
there,
these
yeah.
things that once seemed crazy become like real life thanks to people being willing to take a gamble on it, supported by taxpayer dollars, basically.
Yeah. So when will I be able to be in bed, think I want coffee to automatically arrive on my nightstand, and it arrive? Because I remember the Jetsons. You may be too young for the Jetsons, but it was big when I was growing up, right?
Oh, for sure.
I don't know why I don't have a Rosie right now. I'm just saying.
It's so frustrating. What are people working on?
Right, exactly. They're just trying to cure paralysis and Parkinson's and all of that. That is so motivational. So I can see how it would be easy to go to work every day when you're working on something that is literally changing whole families and their lives.
Yeah,
and, even you think about Parkinson's as people age, the impact in their community, the work that their caregivers have to do to take care of them, the impact on grandkids and things like that. So I could see how that would be very inspiring. And I can also see how the challenges with it, and when things don't work like you expect them to, experiments fail, grants aren't funded,
Absolutely.
You're stressed about being able to fund and keep your research team there. How do you keep yourself motivated during those hard times?
Ooh, that's a really good question. I mean, I think if you're not willing to kind of face failure, academia is not the right game for you,
yes.
right?
Yeah,
you're gonna we're in research, which means you're taking on problems which we don't know the answer to, right? You're gonna fail. You're gonna fail way more often than you succeed. So I mean, I think there's maybe it depends on the type of person. Like I'm motivated by that longer term outlook and that, wow, like we really did something here, and it's okay to me if we failed 20, 30 times on the way there. But, I think the other piece is probably like everybody else, like I get recharged from my family and, getting to, also, one of the things I see about going back and forth between industry and academia, one of the blessings and curses of academia is that we're always mentoring people, and that's I think about what are the parts of my day that I look forward to the most.
Yeah.
And it's those meetings with students, right, where they're scrambling on problems, and maybe they're they just want to discuss something, and it's a lot of fun to see people grow over that 4 or 5 year term when they're getting their PhDs.
Yeah.
The curse of that is that then they leave, and then you're starting from scratch again, right?
You just need to figure out how they could get an extra gold award for that postdoc. That extra credit.
Right. The extra credit postdoc.
Lab, your extra credit postdoc will make more. That is something also that's really important, is that we forget that when we invest. So I say we as a country, when we invest in the future of humanity, one of the ways that we do that is through tax money and other ways is funding this basic
Absolutely.
research. And I think it didn't actually connect to me to think about it this way until you
Sure.
just said this, that we're also investing in every single individual and brilliant mind who's learning from that research that then is going to take it and go somewhere else. And maybe even like you did, go from completely different things and make an impact in another area of the world. So it's also this added benefit of the research funds is also that educational piece that you're talking about.
That's a really good point. We think about kind of, okay, we're funding this research, but it's a 2-for-1 deal, right?
Yeah.
We're training these fantastic scientists. They receive, great training in how to solve problems that we don't know the answer to, and then they go off, whether it's they stay in research, they go to industry, and they can really do some amazing things, life-changing things with those skills that they learn. So it really is a 2-for-1
Yeah,
deal.
it is a 2-for-1 thing. Okay, so first off, I know what you don't do out of work right now. You don't ride your electric
That's
skateboard
right.
anymore. What is it that you do outside of work now?
Lately I've I think mostly gotten into biking, so biking with the kids or on the Peloton or something like that. And yeah, mostly just spending time with the families.
Yeah,
How I recharge.
Yeah. Well, you also said earlier recharge by not chasing
Yeah,
the kids
that's
around
true.
and
That's
going
true.
into work.
Yeah, sometimes work is the escape from having 3 kids means a lot of effort on that side.
Yeah. So what are you excited about in 2026?
Most excited about in 2026? I think maybe one of the things that's maybe flying a little bit under the radar right now is there's been a lot of, I'm talking about brain-computer interfaces and working on them on the academic side. There's been a lot of industry investment in this space in the last 5 to 10 years. People have heard of companies like Neuralink, Elon Musk's company, and they're developing, however you feel about some of those things, they're developing some amazing technologies. And what I'm really excited about, there are other companies as well, really they're going to give us kind of high-resolution access to the brain. So where we've been thinking about paralysis and these are kind of like our first like entryway into treating these neurodegenerative diseases, and there's going to be other things, mood disorders, emotional regulation and things like that I think we can also take on. And so I'm just excited that we're getting a lot of new technologies. There's still a ton of research to do, but it's a really exciting time where it's like before we were like trying to do astronomy without telescopes.
Yes, okay.
And now we've got telescopes, and like now let's go see what's out there in the brain.
Yeah. Okay, that's exciting. So I know that your lab has a website. Can you tell the audience how they can follow the research that you're doing and learn more?
Awesome. So it's the Systems Neural Engineering Lab. That's SNEL.ai.
Okay.
It's a great place to see our work.
Okay, and we will also include that in the show notes. So why don't we wrap this up with, if they forget all the fun that we had in this episode, they should remember to wear their bike helmet. What
right.
else?
That is the key message, absolutely.
Exactly. What else do you want to make sure that they take away from our time together?
Yeah, I mean, I hope people are excited about this idea that things that once seemed kind of intractable, these problems with the brain, we're making progress, and there's a lot of really exciting developments that are really going to affect people's lives, and it all comes from this kind of investment that we've had in, let's support kind of biomedical basic research and just understand things better.
Well, amazing. Well, thank you for the work that you are
so
doing.
Much.
The ability to give people a full life is amazing. So I'm very grateful for that. And that you took time out of your day and said yes to being on the podcast.
I love being
today.
here. Thank you so much.
Amazing. So listeners, thank you for following us. We will put the link to the website so that you can follow Chethan's work in our show notes. If you're interested or you have additional questions, please feel free to leave us comments. And until then, make sure you've taken a moment to subscribe, and we will see you in the next episode of Holy Shift, Biomedical Breakthroughs Shaping Tomorrow. That's it for this episode of Holy Shift, Biomedical Breakthroughs Shaping Tomorrow. If today's conversation sparked your curiosity, pass it along to someone eager to explore the power of research to change lives. As a reminder, the opinions expressed in this podcast are those of the host and guest and do not represent those of any organization mentioned. Be sure to follow or subscribe wherever you get your podcasts so you never miss an episode. To learn more about the research featured on this show, visit bme.gatech.edu or check the show notes for links and resources. Thanks for listening, and remember, behind every innovation is a purpose, a person, and a powerful story.